Hello viewers, in continuation to the previous episode where we have discussed about the fullerene, carbide and chlorofluorocarbon, we shall be talking today about the chlorofluorocarbons, their structure, synthesis and major properties. Further, the comparison between the carbon and silicon, its similarities and dissimilarities will be discussed in detail. What are the silicates? How the silicate structure is based upon various principles. A structure based classification of silicates is taken under presentation today. The chlorofluorocarbon contains carbon, chlorine and fluorine only. The CFCs are unreactive and non-toxic and are widely used as refrigeration fluids, as propellant in aerosol and for washing computer boards. They were earlier known as miraculous refrigerant. It is produced as a volatile derivative of methane, ethane and propane. The most common CFC is dichloro-difluoromethane, commonly known as R12 or Freon 12. These molecules of chlorofluorocarbon are depleting the ozone layer present in the stratosphere. Let us have a brief account of this process. The UV radiation in the stratosphere causes dissociation of CFC molecule producing chlorine atoms and radicals. This is the process how the chlorine radical is being produced, and this chlorine atom then reacts with the ozone like this. It forms the chlorine monoxide, and this chlorine monoxide is continuing as a chain process. The chlorine monoxide radical decomposes slowly, reforming chlorine radical which react with more ozone. This is the process how it is going to form the chlorine radical, and again a chain process is going to continue. There is no effective sink of chlorine radical. Chlorine monoxide reacts with nascent oxygen and reforms chlorine. This cycle continues, destroying the ozone layer. A single chlorine atom can cause depletion of thousands of ozone molecules. CFC causes ozone depletion in stratosphere and increased cases of skin cancer. After Montreal Protocol held in 1987, these chlorofluorocarbons are replaced by the hydrofluorocarbon HFCs like CH2FCF3 and SCFCs hydrochlorofluorocarbons as CHCl2CF3. This is the structure of HFC hydrofluorocarbon 134A CH2FCF3. It is the structure of the hydrochlorofluorocarbon CHCl2CF3, CHFClCF3, CHF2CF3. It is SCFC 125, it is SCFC 124 and SCFC 123. So, these are the hydrofluorocarbon and hydrochlorofluorocarbon which has been better reactivity about that of CFCs. Let us discuss the structure and properties of chlorofluorocarbon. Carbon in the CFC bonds with tetrahedral symmetry. Since fluorine and chlorine atoms differ greatly in size and effective charge from hydrogen and from each other, the methane derived CFCs deviate from perfect tetrahedral symmetry. Generally, CFCs are volatile in nature. Methane boils at minus 161 degrees centigrade, whereas the fluoromethane boil between minus 51.7 and minus 128 degrees centigrade. So, this is the difference between the boiling point of the methane and thereof fluoromethanes. The CFCs have still higher boiling points because the chloride is even more polarizable as compared to that of fluoride. Because of their polarity, the CFCs are useful solvents and their boiling point make them suitable as refrigerant. The CFCs are far less inflammable than methane, in part because they contain fewer carbon hydrogen bonds, and in part because in the case of the chloride and bromide, the released halides quench the free radicals that sustain flames. The densities of CFCs are higher than their corresponding alkanes. In general, the densities of these compounds correlates with the number of chlorides. These are non-toxic and non-inflammable and can be readily converted from a liquid to gas and vice versa. And this is the basic reason why CFC got very wide applicability. The carbon tetrachloride and hydrogen fluoride reacts to form freon. This is the reaction with the carbon tetrachloride and hydrogen fluoride, how the freon is getting formed. Let us have a comparison between the carbon and silicon, because we have discussed a lot about the carbon, the carbides. Further, we have discussed about the fluorocarbon, then chlorofluorocarbon and next to this we shall be talking about the silicates. So, it is essential to understand the similarities and dissimilarities between carbon and silicon. Both have same number of valence electron 4 and hence they have many similar properties. Both have similar electronic configuration of the outer shell, that is NS2 NP2 type of configuration. Both are tetravalent and shows tetracovalency. Both are widely distribution in matter as carbon in organic matter and silicon in inorganic matter. Carbon and silicon both exhibits allotropy, both are non-metals and form oxides, hydrides, etc. Higher oxides of carbon and silicon are acidic in nature. Carbon and silicon both forms dioxide of carbon dioxide, silicon dioxide, acids like carbonic acid, hydrides like methane, SiH4, CH4, halides like carbon tetrachloride, silicon tetrachloride are being formed. Both shows the property of catenation making large compounds. There are certain dissimilarities between the two, the carbon and silicon. Let us have a look on it. Carbon is essential constituent of animal and vegetable kingdom. However, the silicon is belonging to the non-living minerals, ores, rocks, clays and soil. Since they have different number of electrons in penultimate shell, carbon is holding 2 electrons and silicon having 8 electrons in the penultimate shell. So, it makes certain properties to differ from each other. The maximum covalency of carbon is 4 and silicon is 6. The size of carbon atom is much smaller than silicon. Carbon has much more power of catenation, it is much harder and having high melting and boiling point as compared to that of silicon. Due to more power of catenation, carbon is capable to form large number of compounds as compared to silicon. Carbon does not melt at all, but silicon undergoes melting at higher temperature. Carbon tetrachloride is more stable than that of silicon tetrachloride. Similarly, silicic acid is more stable than carbonic acid. Silicon forms a number of cross-linked silicones used as lubricant, repellent, insulator, etc., but carbon does not form such type of lubricant or repellent or insulating material having same nature as silicon has shown. Silica is found in nature in several crystalline and amorphous form and also found in certain plants and animals. Silica is major constituent of sand. Quartz is purest and most common variety of silica. Quartz is colorless and exists as alpha and beta quartz. Because we are proceeding towards the silicates, so it is essential to have a small idea about the silica or the silicon dioxide. Sand is crushed form of the quartz and found in nature due to weathering of rocks. Agate, jasper and onyx are amorphous forms of silica. About 95% of silica is consumed in construction. Silica bricks are used as refractory bricks for lining the furnaces. Colored variety of silica is used as gems. Let us discuss about the silicates. We shall be talking about the structure of the silicates also. During cooling of the earth, lighter silicate materials crystallized and floated to the surface, resulting in the concentration of silicates in the earth crust. About 95% of earth crust is composed of silicate minerals, clays or silica. Thousands of minerals are examples of silicates. Quartz is most common form of silica and is main component of sea sand. Building materials like granite, slate, brick and cement are all silicate including the glass. Silicates are most insoluble and because they have an infinite ionic structure and also due to very strong silicon oxygen bond, the bond energy of the silicon oxygen bond is 88 kilocalories per mole. X-ray diffraction studies have confirmed that in silicates, each silicon atom is bonded to 4 of the oxygen in a tetrahedral geometry and silicon atom is located at the center of the tetrahedron. Any salt derived from silicic acid or from silica is known as silicate. Silicates are chemical compound composed of silicon, oxygen and at least one metal atom. Silicates consist of silicate group either isolated or joined to other groups in chain, sheet or 3-dimensional groups with metal element such as mica or feldspar. The silicate is also defined as the salt or ester of silicic acid with polymeric negative ions having tetrahedral structure of silicate group linked in rings, chains, sheets or 3-dimensional framework. These are the principles of silicate structure. The electronegativity difference between oxygen and silicon is 1.7, as it is written here as 3.5 minus 1.8, their electronegativity value given the difference as 1.7, which suggests that the bond are almost 50% ionic and 50% covalent. Thus, structure may be thought by both the ionic and the covalent concepts. The atoms are packed together or coordinated by the larger anions like oxygen depends on the radius ratio of the cation to anion. The radius ratio of silicon and oxygen is 0.29, which suggests that silicon is 4 coordinate and should be surrounded by 4 oxygen atoms at the corner of a tetrahedron. This is the range of radius ratio 0.732 to 0.414 have the coordination number 6 and type of hole occupied is octahedral, and in our case here it is ranging between the 0.414 to 0.225 with coordination number 4 and the type of hole occupied is tetrahedral. So, this value is 0.29 lying well in this region. It can be equally predicted by use of 3s and 3p orbital by silicon for bonding. Thus, silicates are based on silicate tetrahedral unit. The silicate tetrahedra may exist as discrete units or may polymerize into larger units by sharing corners, that is by sharing the oxygen atoms, because oxygen atoms are placed at the vertices. The oxygen atoms are often close packed. Close packed structure have tetrahedral and octahedral holes, and metal ions may occupy either tetrahedral or octahedral sites depending on the size. Most metal ions are the right size to fit one type of hole, though aluminum ion can fit into either. Thus, aluminum can replace either a metal in one of the holes or a silicon atom in the lattice. It is significant for aluminosilicate. This is the structure of silicate. It is the bond length 162 picometer and it is the angle oxygen silicon oxygen axis 109 and 0.5 degree. This is the silicate oxyanion. It is the first category of the silicates based on the structure. It is nesosilicate, also known as orthosilicate or Iceland silicate. In Greek, neso means Iceland. It has orthosilicate ion which constitute isolated silicate tetrahedra that are connected only by interstitial cations. If the corner oxygens are not shared with other silicate tetrahedrons, each tetrahedron will be isolated and it gives rise to Iceland silicate group. The basic structural unit is then silicate. In this group, the oxygen are shared with octahedral groups that contain other cations like magnesium ion, ferrous ion or calcium ion. For example, olivine group where forsterite Mg2SiO4, phyllite Fe2SiO4 and in the garnet group the nesosilicates are present known as grossular or Ca3Al2SiO4 whole thrice. Olivine is also found in meteorites and large grains have been reported in many of them. Forsterite and olivine can be olive green to light and dark green, yellow green, yellow brown and brown. Pure forsterite is colorless, but this is extremely rare. Phyllite is usually yellow brown to brown in color. It is the zircon, which is a gemstone and looks like a diamond. Garnet looks like a red gemstone and it is the presentation of the unit cell geometry of olivine material as which is applicable for forsterite or phyllite. Here the dots of red color are for oxygen, then magnesium or iron are presented by the golden color dot and blue color is dedicated for the silicate tetrahedra. And it is the gemstone zircon which is made by heat treatment under reducing condition, this beautiful gemstone of blue color. Zircon is in fact zirconium silicate. The crystal structure of zircon is tetrahedral. Natural color of zircon varies between colorless, yellow golden, red, brown, blue and green, and the color of zircons can be changed by heat treatment. The brown zircons can be transformed into colorless and blue zircons by heating to 800 to 1000 degrees centigrade. Colorless specimens are a popular substitute for diamond known as Matura diamond. It was a brief account of nesosilicate. The second category is of sorosilicate, also known as pyrosilicate, disilicate or double Iceland silicate. The term sorosilicate origins from the Greek, where soro means heap, amount, have isolated double tetrahedra group with ratio of silicon to oxygen 2:7. If one of the corner oxygen is shared with another tetrahedron, this gives rise to the sorosilicate group. It is also called double Iceland group because there are two linked tetrahedrons isolated from all other tetrahedron, only two are running together. This is the basic structural unit Si2O7 having 6 negative charge. Hemimorphite Zn4Si2O7 OH whole twice H2O is the sorosilicate type of mineral. Some sorosilicates are a combination of single and double Iceland. It is the structure of the sorosilicates. It is attached together through the oxygen and only two silicates are attached together. It is the example of the epidote. The third category is the ring silicate or cyclosilicate. The cyclosilicates have linked tetrahedra with SiXO3x with 2x negative charge, that is indicative of the ratio of silicon oxygen as 1:3, mainly exist as 3-member and 6-membered ring. If two of the oxygens are shared and the structure is arranged in a ring, it gives rise to the cyclosilicate group or ring silicate. The best example of the 3-member ring is benitoite, it is BaTiSiO3O9, and the 6-member ring is beryl or emerald. Beryl and emerald both are gemstone having pale green and strong green color respectively. The benitoite is a rare blue barium titanium silicate mineral. It is found in hydrothermally altered serpentinite. It fluoresces under short wave ultraviolet light, appearing bright blue to bluish white in color. This is the 6-membered ring of beryl. It is the gemstone emerald of green color and it is a bright yellow golden color of the beryl gemstone. It is all having this structure, the ring silicate or cyclosilicate. The fourth category is of N-silicate, where the single chain and double chain silicates are found. The N-silicate, where N means fiber, have interlocking chains of silicate tetrahedra with SiO3 or a ratio of silicon to oxygen is 1:3 for single chain silicate. Next to this there is double chain silicate. Let us discuss first for the single chain. The two of the oxygens are shared in a way to make a long single chains of linked silicate tetrahedra. The basic structural unit is Si2O6 with 4 negative charge or SiO3 with 2 negative charge. Best examples are pyroxene group as anstatite MgSiO3 or ferrosilite FeSiO3. Not only pyroxene, but pyroxenite group where wollastonite is the best example, the calcium silicate is present having the single chain type of silicate structure. It is the formation of the single chain silicate, it is the pyroxene group and this is the presentation of the wollastonite mineral having the single chain structure. The double chain silicates have interlocking chains of silicate tetrahedron with Si4O11 or a ratio silicon to oxygen as 4:11. The double chain, when two chains are linked together in such a way that each tetrahedra group shares 3 of its oxygens, means all the 3 oxygens are getting utilized. The basic structural group is Si4O11 with 6 negative charge. Amphibole group is having the double chain structure and best example is comingtonite and termolite. This is the double chain silicate structure. it is the structure of termolite. This is the way how all the 3 oxygens at the corners of this tetrahedral has been attached with the other tetrahedron, making the 2 chains the double chain silicate. The next category is of phyllosilicate, which has sheet like structure. Phyllo represents in Greek to leaf. It forms parallel sheet of silicate tetrahedra with Si2O5 having silicon oxygen ratio 2:5. All phyllosilicate minerals are hydrated with either water or hydroxyl groups attached. The phyllosilicate appears when 3 of the oxygens from each tetrahedral group are shared in such a way that infinite sheet of silicate tetrahedra can be prepared. In the previous case of the double chain silicate, the 3 oxygens are being shared, but a chain is being formed. Here the 3 oxygens are shared and a sheet is being formed. Basic structural group is Si2O5 with 2 negative charge. Micas like muscovite and margarite, the clay minerals like kaolinite, pyrophyllite, the chlorite, talc what you call the talcum powder, and serpentine minerals are the best examples of phyllosilicates. It is the structure of biotite. In biotite, aluminum is substituting for silicon in one of the tetrahedral group. The another example is the talc, the talcum powder. It is the formula Mg3Si2O5 whole thrice and OS twice. This Mg2 plus and hydroxide ions lies between the silicate sheet. The slippery feel is due to the sliding of the silicate sheet relative to one another, which gives that substance its lubricating properties. The phenomena is somewhat similar what we have discussed about the graphite. Graphite is having the layered structure and the 2 layers are held together with very weak van der Waals forces. So, it slides easily. The similar type of structure is there with talc, where the sliding of the silicate sheet takes place. It will be better explained with this structure. It is the structure of the sheet silicate, the pyrosilicate, where a single leaf like sheet is being established. It is the structure. It is the kaolinite, the clay, and this is the structure of the talc, where the silicates are going to sandwich the middle layer. This layer is of the magnesium ion and that of the hydroxyl ion. So, these 2 layers are sliding one over another about this sandwiched layer of the magnesium ion and the hydroxide ion in the talc, and that is why the lubricating property is appearing. The kaolinite is made up of many micelles piled one atop the other. Since the surface on one micelle contains hydrogen ions and the other surface only oxygen ions, there is a tendency for hydrogen bonds to form between the micelles. Thus, micelles are very strongly bonded together due to the hydrogen bonding and nearly impossible to separate. Thus, kaolinite is known as non-expanding phyllosilicate. Since each micelle is constructed of a layer of silicon tetrahedral units and a layer of octahedral units, the kaolinite is called 1:1 clay mineral. Thus, kaolinite is a 1:1 non-expanding clay mineral. The another category is of tectosilicate, which is having framework silicate like structure. When all corner oxygens are shared with another silicate tetrahedra, then it gives rise to framework silicate. The basic structural group of tectosilicate is SiO2. The best example is quartz, cristobalite and tridymite. In tectosilicate, if some of silicate ions are replaced by aluminum ion, then a charge imbalance arises and permit other ion to get coordinated in different arrangements within the framework structure. And the best example is feldspar and feldspatite. It is called the framework silicate because its structure is composed of interconnected tetrahedrons going outward in all directions, forming an intricate framework analogous to the framework of large building. If a silicon tetrahedra shares all its 4 oxygen with other tetrahedrons giving a silicon to oxygen ratio 1:2, it results in a 3-dimensional framework structure. This is the structure of quartz, and it is the beautiful structure of tectosilicate having the framework structure. This is the structure of the feldspar. Again, it is representing the 3-dimensional structure, the framework type of silicate. This is the feldspar structure. So, we have discussed about the chlorofluorocarbons, how the chlorofluorocarbons are moving towards the stratosphere causing the depletion of the ozone layer. We have discussed brief account of the synthesis and some of the major properties of chlorofluorocarbon. Since the associated compounds of carbon and silicon are under discussion, so a brief account of similarity between carbon and silicon and dissimilarity due to the arrangement of electron in the penultimate cell has been discussed. Further, what are silicates, how the different kind of silicates originates due to their structures, how beautifully the gemstones are constituted by the silicate minerals. In the next episode, we shall be talking about the halogens in complete detail, and it will be also discussion about the tetrasulfur compounds. Thank you.